Now, one of the most useful rules to help you integrate functions is something known as substitution. Now, to explain what substitution is, we first need to remember a differentiation rule called the chain rule. And the chain rule says if you have a function nested inside of another function, you can take the derivative by taking the derivative of the outside, preserving the inside as it is, but then multiplying by the inside. Now, this can also be reversed. If I were to integrate both sides of the formula, and I can write the right-hand side on the left, this would be the integral of f prime of gx times g prime of x. Well, that would have to be the left-hand side. And notice that we have the integral of a derivative, so they basically undo each other. The resulting function is f of g of x plus c. Now this is something called substitution, as I said. It's just basically the reverse chain rule. And the substitution rule gets its name from the mechanism that we usually use to actually do this. Rather than dealing with F's and G's, we usually use the letter U. And let me show you how that works. So you'll notice that you have here a g of x and a g prime of x dx. And what we'll usually write is let U equal g of x. Then the derivative would be du dx would be the derivative of g of x. And then finally, what we'll actually do is we'll take this dx and write it over here on the right. And the reason why we do that, and first of all, let me show you what that would look like. So the dx gets moved to the right. So here is my dx on the right. And the reason why we do that is it gives us a very clean way of rewriting our integral to help us see how to integrate it. And so what has happened is this left function, the integral of f prime of, and then the g of x has been replaced with a u. And then the g prime of x dx has been replaced with the du. That would equal, on the right-hand side, f of, and then, again, on the right-hand side, we have g of x, which we would simply write as a u plus c. And that seems pretty straightforward because it's simply saying, hey, the integral of the derivative of f, where u is the variable, is the original function u. So it would be very easy to recognize how to integrate the function once this process is completed. And so to see how this works, let's actually work an example. So here is my first example. We have the integral of 4 times quantity 3 plus 4u all squared, 3 plus 4x all squared dx, and we're told to find it, of course. Now, there's a couple of ways you could do this problem. You could do this problem without substitution, certainly. You could solve it just simply using algebra. You could rewrite 3 plus 4x all squared simplifies to 9 plus, that'd be 2 times 3 times 4, because there'll be 2 copies of it, that's 24x, plus 4x all squared would become 16x squared dx. And then we'll distribute out that 4. to get 36 plus, and you're already seeing the downsides of this. 24 times 4, I guess that would be 96x plus 16 times 4 would be 64x squared dx. And that integrates to 36x plus, the x becomes x squared, so we'll divide by 2 to get 48 for the new coefficient. And since 64 does not divide evenly by 3, that would be 64 thirds x cubed. Since the square becomes a cube. And of course we integrated, so that's plus c. And there's my final answer, but it's not ideal because we had to integrate and we had to do a lot of algebra to do that integration directly. And we don't want to do that. We would rather have a more elegant way of doing this. So that's the algebra method. All right. Let's actually do it using substitution now. So let's move over just a little bit. So I'm going to rewrite the original problem for quantity 3 plus 4x all squared dx. And when doing a problem involving substitution, it's all about finding out what your u is going to be. And usually, if you think that substitution is the way to proceed, you're going to want to find the most complicated innermost function. So in this case, I see a 3 plus 4x that's being squared completely. And seeing all that together makes me think, let's let u equal 3 plus 4x. Now, if my u is equal to 3 plus 4x, then I could take the derivative of both sides, du. Now, normally we would write that du dx to say the derivative of u with respect to x, but it just turns out to be handy when doing substitution problems to just write the dx on the other side, as though it were a fraction, because derivatives act a lot like fractions for various technical reasons. So now, but you take the derivative the same way you do normally, so what we're going to get on the right-hand side is 0 plus 4x becomes a 4. Now, of course, we have a 0, so we can just get rid of all that. So my du is equal to 4 dx. Now, often you're going to do these problems, and it's going to be very nice because you're going to see your derivative, 4 times dx, show up elsewhere in the problem. So here it is together, 4 dx. Now what does that do for us? Well, let's see here. My 4 dx, I'll do this in black. My 4 dx gets replaced with a du. So that's the 4 dx right there, becoming a du. And then we still have the parentheses and the square. However, the 3 plus 4x should be replaced with a plain old u. So what does that do for us? Well, let me just rewrite this a little more succinctly. I'm just being asked, what's the integral of u squared with respect to u? So we just treat u as our variable. And the integral, of course, of u squared is 1/3 u cubed. So what else am I forgetting? Well, of course, there's always a plus c. I just integrated. But this is not my final answer because, well, heck, I made up u. U is my thing, right? You can see up here where I let u equal 3 plus 4x. And that's something I made up. The guy asking me the problem has no clue what my u is. So what do I have to do? Well, I just have to substitute back for that u. So to finish off the problem, I will rewrite this. This will be 1/3, and u will get replaced with, in parentheses, 3 plus 4x, and the cube stays there, plus c. Now, I want to point out that this looks different. This is my final answer. And it looks different than the answer I got before, at least at first. However, I promise you, if you were to actually do the algebra to simplify the answer here on the right, it would actually end up being exactly the same as the answer on the left. Both answers are the same once the algebra is done, but I love this method because it's so much easier to do the problem without doing all the fancy algebra. All it requires is a clever substitution. And we'll see some other problems later where, in fact, substitution is not just useful in making the problem easier, it actually makes the problem possible. Not all problems can be done without using substitution, as we did using the algebra method a moment ago. But we'll do that in a future video.